So we just used the fact that vector operators transform like vectors under rotations to show that they must have these commutation relations with the angular momentum operators, the angular momentum being the generator of rotations. And that's pretty much all we know about angular momentum. It must be a vector operator itself, and indeed you can show from the properties of rotations that it does indeed obey these equations. And in fact, these commutation relations tell us an extraordinary amount about angular momentum. So in some sense, if you have a vector operator, you have three components to it, say an AX, an AY, and AZ. So for our vector operator for angular momentum, we have a JX, JY, and JZ. And so it's fairly clear what we mean by the dot product of that, which is also sometimes written as J squared, which is clearly just the sum of the squares of the individual components. So this is just an operator. Now if we have a look at the eigenvalues of this is in some sense the total amount of angular momentum you have, irrespective of the direction. If we have a look at the eigenvalues of this is Hermitian because each of these elements are Hermitian, so the eigenvalues are real, and this is in fact an observable, so you can in fact measure this. And so it must have a complete set of eigenstates, and we'll call those eigenvalues, say, lambda. There we go, so we're labeling them by the eigenstates. So there might be more than one degenerate value, but we'll ignore that for now. Okay, now more interestingly, if we take any component of our angular momentum and we take the commutator with j squared, then we're going to get 0. So supposing we would take jx, obviously jx and jx squared commute, because it's just jx cubed minus jx cubed, but jx and jy squared and jx and jz squared do not commute, and so we're actually going to get non-zero terms there, but they turn out to be equal and opposite because of this anti-symmetric operator here. So let's go through that in detail. So there we're using the Einstein summation notation. Now we know what this is. Where I've introduced Einstein summation notation over P as well. Now once again, just remember the properties of the anti-symmetric tensor, the Levi-Civita tensor. Just remember it is 1 if these indices are an even permutation of 1, 2, 3. It's -1 if they're an odd permutation of 1, 2, 3, and otherwise it's 0. What that means is if I have, even with arbitrary indices there, if I swap two of the indices, any two of the indices, I'm going to get a minus sign. And I can use that very heavily in situations where I'm summing over these indices because I can relabel indices because they're dummy indices. So we can use that here. You'll note that we're summing over m and p here, but we've got p and m in this order, and we're summing over m and p here, but we've got m and p. So they're in the wrong order. So these things, since they don't commute, as we know, we can't just swap them. And if we did, then we'd end up with a factor of 2. But we can swap them if we relabel m and p. So I'm going to relabel p to m, and I'm going to relabel m to p. And so now you can see that we're summing over the same kinds of terms there. But now these two terms are different, but you'll note that they're only different by a flipping of an index. So if I swap those two indices, I'll get a minus sign, and they'll be exactly the same, and so I'll end up with 0. And so the commutator of any component of the angular momentum and j squared is 0. And what that means is that they must have identical eigenstates. So an eigenstate of j squared is going to also be an eigenstate of any element of the angular momentum operator, and vice versa. So there definitely is some kind of potential degeneracy there. If we apply jz, z is an arbitrary choice, but one that's very popular in the literature. If we apply jz to our lambda, then there should be some other potential eigenvalue, which we'll say is m h bar. The h bar is just to fit in with convention. And so there's two eigenvalues. There's the lambda if you apply j squared, and there's the m h bar if you apply jz. And there's in fact a relationship that we can work out between them, again just using the commutation relation. So j squared minus jz squared is, by definition, and if we take the expectation value with respect to these eigenstates on both sides, then on this side, because we take any square operator and take the expectation value of anything, then that is just the inner product of a state and itself, and therefore we've already shown that that must be greater than or equal to 0, so this is all greater than or equal to 0. J squared acting on this just gives us outer lambda, and then we've got the inner product of these two, which is by definition 1. Jz gives us mh bar, do it again, we get another mh bar. And we've got a relationship between lambda and m. You can see that m, the magnitude of m, is bounded by lambda. We can go even further in figuring out the relationship between lambda and m by investigating what's called the raising and lowering operators. There's two of them. One is a raising operator, it's denoted plus, and one is a lowering operator, denoted minus, and they're simply defined as that linear combination of jx and jy. And because we know all about how jx and jy and jz commute from our commutation relations, we can easily show the following properties, which I recommend you do. This one simply says that if you apply j plus or j minus to one of our eigenstates, lambda m, then you don't get to change lambda. And the other one is that, which simply says that if you apply j plus or minus to the eigenstate lambda m, then you raise or lower m by 1, with the raising operator raising m by 1 and the lowering operator lowering m by 1. But you can't raise or lower m arbitrarily because m squared is bounded by lambda. And so if you do the algebra, you show that this train of raising and lowering m must abort at some maximum and minimum value of m, and that maximum and minimum value is given by j, where the eigenvalue lambda is defined as j plus 1 times h bar squared. So hopefully that spectrum of eigenvalues is familiar from previous examinations of angular momentum, but we've shown here that this comes straight from the definition of angular momentum as the generator of rotations, which then gave us the commutation relations. And those commutation relations tell us that this is always the spectrum of any kind of angular momentum.